Hello, welcome to Mystery Science. Today we're going to be doing the required practical for Newton's second law. We're going to prove that force is proportional to mass and acceleration. To do this experiment you're going to need a bunch of kit. You're going to need a ramp that you can adjust to get the right height. You're going to need a pulley to attach on the end of a bench, and you're going to need a dynamics trolley and some teeny tiny 10-gram masses. The reason we're going to use 10-gram masses is because 100 grams is roughly equivalent to 1 Newton. So this, if I let it fall, has the force of 1 Newton. So each one of these little ones is going to be the force of 0.1 newtons, roughly, if we use g, the acceleration due to gravity, to be 10. What you want to do is you want to make sure that your pulley is as frictionless as possible. We're going to try and eliminate friction. There's going to be some friction in this experiment, and there are some things you can do to mitigate that friction and to try and get rid of it. So first thing you want to do is get your pulley attached to the end of your bench. Take your dynamics trolley with the string attached and place it at the center of your ramp and try and get it so that it is lined up as much as possible. Now we're going to want a start position where the string is just above the end of the pulley. So make sure your loop is as close to this distance as possible. You place on your masses, and that should allow your trolley to accelerate. Now, a couple of things with this. If you look at the trolley, it's currently independent of the mass. If I push it, set the string out of the way, if I push it, it's going to slow down. And it slows down because there's a friction force on my trolley. This is no good. I don't want a friction force on my trolley. I want it to kind of roll without speeding up and slowing down, so we have to raise the ramp slightly. So in order to do that, we're going to use a couple of different bits of equipment. Take a couple of masses. You can use a book, you can use anything really, but I think masses have been the best thing I've found so far. Put a couple in either side. You're just trying to raise the ramp enough so that when you push the trolley, try and get it central, it does not slow down or speed up. If you put too much of a slope on it, you'll end up with an acceleration due to gravity. Okay? If you let it go, it should not move, but if you give it a force, it should move and stay roughly the same speed. There we go, I'm quite happy with that. The reason it keeps stopping abruptly is because I keep letting it run over the string. But if you're doing the experiment properly, that won't be an issue. Another thing that's useful is a piece of carpet. This piece of carpet, if you place it at the bottom, instead of getting a large crash when the mass hits the floor, you can have a nice kind of soft thud. So I take my 100 grams or my 1 Newton mass and I attach it to the string. It's useful to have some way of stopping the trolley from moving while you're doing this. Okay, now the distance this is going to move is the distance from the top of the mass to the floor, where it's going to hit the floor. So what's going to happen is as soon as I let go of this trolley, it's going to accelerate. I'm going to mark starting position so that I get it the same each time, and I'm going to make sure that the knot just tops the pulley here. That way it's always going to be exactly the same. Okay? We can see already where some errors are going to be creeping in with this method. But in principle, now when I let this go, I had a stop clock, I would start the stop clock as soon as I let go, and then stop it as soon as it hits the floor. With doing this, this means that it's accelerating just through that little distance there, and it should come back to the same starting point each time, and then you do a number of different tests to get an average. So that was test run number 1, test run number 2, stop the stop clock, stop the stop clock as soon as it hits the floor, then you do your third run, start, stop. So in order for this to work well, you need to know the mass of the trolley. Okay, once you've done your 3 readings, you can then remove 0.1 newtons from your force. However, when you are accelerating the mass of the object, you're accelerating this mass, but you're also accelerating this mass. This mass is pulling down or being pulled down by gravity. Therefore, we need to keep the mass constant, which means that when we change our mass, we need to make sure that whatever we take off our pulley mass goes back on the trolley. You can affix that on there with blue tack. So then we do the experiment again, and we do the same number of readings as before, and we get an average. We're going to start our stop clock, end it when it hits the floor. We're going to use a meter ruler to measure the distance that our dynamics trolley is going to be accelerating through. So we take our trolley back to its starting position. We make sure the masses are attached so that the string is taut. And so we know that this is the distance that it's going to travel. However, if you measure this distance from here to the end of the ramp, that's going to be incorrect. And the reason it's going to be incorrect is because we have to stop timing when the masses hit the floor. We want the acceleration, not just the velocity. So the acceleration is only occurring when the masses are falling. So as soon as you let go, if you have them up at the top here, as soon as you let go, the masses start falling, and then they will hit the ground about there. So that's the distance you want. So the best thing to do is measure the distance that it's actually going to fall using your meter ruler. So it's going to start from the base to the base. So what we do is we kind of lock off our dynamics trolley. We come to here and we take the reading. Remember to include the carpet. And it's going to go to the base there. And so this is going to travel 42 centimeters or 0.42 meters. So we write that down on our data, 0.42 meters. That is the distance that it's going to travel every time. So we measured that distance, it's 0.42 meters, but of course this is going to be a slight error because every single time, unless I get it to the exact same position, I'm going to have a slight error. That distance is going to be slightly different each time. So if you're doing this with more than one person, the best thing to do would be to measure the distance each time just before you release it, and then you can calculate your acceleration with the equation I'm going to show you later, and then you can calculate and get an average of those accelerations. So this is the basic setup. This is what you do on an absolute basic level. You don't need light gates for this, but if you want to do the data more accurately, you're not relying on measuring this every single time. You want to make sure that you're timing between fixed points. You've obviously got a systematic error starting and stopping your stop clock. You have to rely on humans knowing whenever you let go and when has that hit the floor. That's not the most efficient way. So we're going to do this experiment again using data loggers. Okay, so now we've changed our setup slightly. We've got this apparatus here, which is boss and clamp stands with a clamp and a light gate attached on this side. This one is the second light gate, so I'm going to plug this into port B of my data logger. It's very important that you get these the right way around. I've got another clamp here with another boss attached to another light gate. This one is the first one on the run, so this one is attached to A. So the settings on the data logger are quite simple. So for this one we're using a vlog. What I have is I've gone into timing mode. I don't want easy log or anything like that. We've got the timing mode. I'm going to time the acceleration. Now some of these Windows data loggers aren't able to do the acceleration, but you can measure the speed at both points. And if you measure the speed at both points, the distance between them, then you can calculate the change in velocity and the time between them. Now, so this one can accelerate calculate acceleration. I want acceleration A to B, and I'm attached an interrupt card to my dynamics trolley, and I've measured this, and this is exactly 100 millimeters. So in my data logger, it asks me, well, how long is your interrupt card? And I've said 100 millimeters, and this allows it to calculate the speed at this point, because it's going to time how long it takes to cross the light gate, and then it's going to take the speed at this point, and it's going to calculate the acceleration between them. Everything else is the same. I have my masses underneath my ramp just to lift that up slightly so that I'm mitigating as much friction as possible. I'm using the same starting point, so that's where it's going to start from. I'm going to let it build up a little bit of velocity first, so it's going to start accelerating, then it's going to start reading there. I've placed this one such that the distance it takes for the mass to fall to the floor is less than this distance, so it should be accelerating after the card passes this side, and that's so that I don't get any error, I don't get any bumps or interrupts when the masses hit the floor. I've seen so many students get it wrong at this point, and they try and get this as wide as possible, and their dynamics trolley is just simply not accelerating anymore. It's just moving at a constant velocity, or friction is actually slowing it down, so it's decelerating, and that's not what we want. Couple of tips and tricks here. When you've got your wires attached, these can be quite fiddly and they can get in the way. Try and get your light gates as far over the track as possible so they're in the center. This for me means that I've used the little metal struts right on the edges of the clamps. I've tried to keep the clamps parallel, and I've got them pushed right up against the ramp. Okay? There are obviously physical limitations here. Now then, the next thing I'm going to do is make sure my interrupt card is as straight as possible. What tends to happen is they tend to fold over and flap over, and if your dynamics trolley isn't set to be perfectly straight, what's going to happen is the interrupt card is going to crash into one of the light gates, and it's going to mess up your readings. You want the dynamics trolley to go straight as possible, so make sure that you have a line of the string, and it's going through the center of your light gates. Okay, my light gates have got screw threads at the top there, and that's brilliant because now I can line up my string with these lines, and they're pretty much bang on. So we make sure this is as vertical as possible, and we want to be in the same conditions every single time. So I've got my mass attached at this end. I've got a kilogram of mass right there, just to use it as a chock, just to stop that from moving until I want it to. Now then, I've also seen students do this. The students will have something stopping the trolley from moving, and they will just simply pull them away. And that kind of jittery start causes another issue. So to minimize as much error as possible, what I like to do is put my finger firmly onto the dynamics trolley, take the mass away, feel that resistance, know that when I let go it's going to accelerate, make sure my wires are clear of the track, and that can be a little bit fiddly, and then let go. And there we go. So I now have an acceleration there of 0.92 meters per second squared. I'm going to do a couple of those for each mass on the end of my load. But I'm also going to remember that I need to add the mass as I remove mass from this end to add it to the trolley. So I'm going to do a few more readings and then we're going to analyze the data. Now then, a couple more hints, tips and tricks to get this right. When you're returning the trolley from this point to here, it's very useful not to go through the light gates. It's quite tempting just to line it back up and drag it back through. Unfortunately then you start triggering the light gates and then this can confuse the data logger, and if it starts confusing the data logger then things start to go badly wrong, and yeah, this causes a bit of an issue. So you have to make sure you've got exactly the same conditions, make sure your trolley is going to go straight. It can be useful to avoid crashes to put something here that would stop the trolley or slow it down before it crashes. Just make sure that in doing so it's not going to stop this light gate from recording the motion. Okay, so I'll show you what I mean. If I'm going to take this mass away, I could put it back there, but then there's a risk that that's going to crash into there and spill all over the place. If you've got more than one student helping you, you can have somebody on the other side making sure to keep their feet well clear of the masses as they fall down to catch the trolley so that you don't have to keep setting up all over again. Okay, so to get perfect data runs, it does take a little bit of fiddling just to make sure that each run is perfect. That's why I recommend doing 3 repeats and not 5. I know some places like to do 5 repeats for all of their experiments. As long as it's an odd number, I would stay with 3. I certainly wouldn't go up to 7. And that's basically just because this is a little bit fiddly to do. And I've seen students really struggle to get to grips with what's going on here and what they're doing. Okay, remember to try and start from the same position all the time. It doesn't matter as much with the data loggers, but it's really useful to try and keep as many variables controlled as possible. So I found it useful in the past to make sure that I do a couple of dummy runs. Just keep running it through, try and get a consistent value for acceleration. Once you're happy, then I start taking readings. So just keep going, go back with the setup, make sure you're happy with how it's all set up. And then once you get comfortable, then we can start taking some readings. There we go. I'm now getting some pretty consistent results. And so now I'm going to get on with the job of taking some readings. So I'm going to use 5 masses. I'm going to use 100 grams, which is 0.1 of a kilogram, and then I'm going to use 0.08 and 0.06, 0.04 and 0.02. So that's 100 grams, 80 grams, 60 grams, 40 grams and 20 grams. So this is quite simple in newtons. That's 1 newton, that's 0.8 newtons, 0.6 newtons, 0.4 and 0.2. Right, off to do the experiment then. Okay, so after the experiment, these are the accelerations as collected by the data loggers. So what I'd like you to do now, pause the video and calculate those averages. So the average for the first one is 0.925. The average for the second one is 0.716. Average for the third one, 0.550 is 0.368. Now we can choose what to do here because we have a clear kind of outlier from these two points of data. Now you can either circle this as an anomaly and ignore this, or you can add it into your average. Now I think it's pretty close, but I'm going to ignore it. I'm going to circle it and label it as an anomaly. And that makes the average 0.183 plus 0.182, all divided by 2, which is 0.183. Okay, so in each of those cases, I've rounded to the third decimal place. Right, so what do we do with these numbers? Right, so we're going to plot our graph. Okay, so I'm going up 5 squares because I'm going to put force on my y-axis, and I'm going to go from 0, 0.2, 0.4, 0.6, 0.8 and 1 Newton. My acceleration, I'm going to go from 0 up to 1 meters per second squared in steps of 0.1. So I'm going to use 10 squares. I go 0, 0.1, 2, 3, 4, 5, 6, 7, 8, 9, and 1. Okay. So now we add our axes. So this is 0, 0.2, 0.4, 0.6, 0.8 and 1.0, and this is force in newtons. Okay. And down here we're going to have 0, 0.1, 0.2, 0.3, 0.4, 5, 6, 7, 8, and then 1.0. And this is acceleration. meters per second squared. Okay. So what I'm going to do now is I'm going to plot my points. I have my axes. I'm going to plot the point from the data that we've just got. I'm going to start at point 2, and my data starts at 0.183. So that's down about here. If that's 0.1, 0.15, that's going to be 0.18. So I put a clear point right there. At point 4, my data says 0.368. I'm going to round that to 0.37, which is 5, 6, 7, right about there. Then we have at 0.6, 0.55. 0.55 is right there. Okay. 0.8 is 0.716. So I'm going to round that to 0.72. And then 1 Newton, it was 0.925, so I'm going to call that 0.93. Okay, so hopefully you can see we have a nice straight line, a proportional relationship. Now for experimental data, that's actually quite pleasing to see. If we put a ruler against it, we can see that it's not quite straight. Now then, whenever you are using or doing this, it's better to have a clear ruler. Unfortunately, I've only got this green one, which is lovely. However, it's not clear. And the reason you have a clear one is so that you can try and get as many points on both sides of the line. Now, I know that I want an intercept through 0, okay, but I can't let that bias me. If I can get a better line without going through 0, then that's what I should do. And actually, it doesn't look like I can, which is fantastic. So I'm going to kind of go through 0, and I'm going to draw my line of best fit. I'm going to choose it across there, draw it lightly, and that looks pretty good. Right, so I have a line of best fit. I'm pretty pleased with this. Well, what now, Mr. E? Well, now we have force plotted against acceleration, and you can see, as we discussed last time, it is a proportional relationship. It's a straight line. So I can take the gradient from this graph. So I am going to go from here, and I'm going to take it down to here. Okay. So now I simply find out my difference in the y direction and my difference in the x direction. So I know I've gone from 0.2 to about 0.8, 0.9, 0.92, 0.94, 0.96. Okay, so I'm going from 0.2 to 0.8 to 0.9, but because I started from 0.2, I'm going to take 2 off, so that would be 0.7, 0.72, 0.74, 0.76. So my difference in the y-axis is 0.76 newtons. My difference in the x-axis, I'm going again from 0.9 and I'm going off to 0.2, so that's a difference of 0.7, and then each one of these squares is 0.01, so 0.72. Okay, so now I do a little bit of maths. To find the gradient of a graph, I do the difference in y divided by the difference in x. So that's, so that is, the difference in y divided by the difference in x, which is dy by dx. That's just a fancy schmancy way of writing difference in y divided by difference in x. When you get to do advanced algebra, you'll see that this is actually the symbol for differentiating as well. And that is where things get a little bit scary. We have 0.76 divided by 0.72. So this gives me a gradient of 1.06. Now what is the unit for this? If I have, okay. Right, now we know that Newton's second law says that force is equal to mass times acceleration. So this difference in y is a force, this is an acceleration, a force divided by an acceleration, force divided by acceleration gives me the mass. So therefore my mass of the trolley and the masses attached must be 1.06 kilograms. Okay, so the whole point of the required practical is to prove to you that force is proportional to acceleration and that the gradient of this graph is equal to the mass of the trolley. Now, if I look at the mass of my trolley, I can actually find that it is in fact 1 kilogram. And then I added 100 grams on top of it, so that gave me a total mass of 1.1 kilograms. So we are pretty darn close. Well done, us. And that's it. That's all you have to do. That's better. And that's it. That's all you have to do. You just have to draw this graph, prove that force is proportional to acceleration, and you can find the mass of the trolley. You can also do this with the mass. If you change the mass and plot it against the force, you will find the acceleration changing.